Boa tarde a todos. Hoje a gente tem o prazer de receber aqui o Guilherme Limberg. Ele fez a graduação em astronomia aqui no IAG-USP e agora está finalizando seu doutorado sob a orientação da professora Silvia Rossi. Em outubro desse ano, começará o seu pós-doc independente na Universidade de Chicago. Muito obrigada.
Obrigado, professor. Eu falo inglês ou português? Tá bom. Hi everyone, I think everybody here knows me. My name is Guilherme. I am finishing my PhD, just like Professor Angela just said. I'm finishing my PhD here at IAG, I hope in the next 2 months. And I'm starting in October. I have signed a contract, so I cannot delay this. I'm starting an independent postdoc at the University of Chicago. And it's kind of funny that this talk is about stars and galaxies, but somehow I have been hired by the cosmological physics department somehow. But anyway, so yeah, this talk is going to be about galaxy evolution at small scales, meaning galaxy evolution of dwarf galaxies, and specifically how we can learn something about galaxy evolution in this regime of dwarf galaxies using Milky Way satellites, but specifically using Milky Way satellites that are ongoing or like have already gone through tidal disruption. And just to begin, so I want to begin with the figure that was in the background of the first slide. So this is a scheme of an edge-on view of the Milky Way. The Milky Way has not only its stellar disk that has like about 40 kiloparsecs in diameter. Here's the location of the sun. But around the Milky Way disk, we have what we call the galactic halo, which is composed of like, well, its stellar component is made of a bunch of like debris from tidally disrupted satellites. So this is how halos around massive galaxies form in general, is by accreting several dwarf galaxies throughout the history of the accretion history, and then the debris end up like being associated with the halo of these massive galaxies. But not only we have a bunch of disrupted dwarf galaxies that are occupying this galactic halo, we also have intact surviving galaxies, intact satellite galaxies, like for instance for the Milky Way, the LMC and the SMC, which are 2 examples of dwarf galaxies that have been known since antiquity. And I'm going to start by going through several disrupted accreted dwarf galaxies that have been discovered throughout the history of, history of astronomical surveys. And specifically, this is not going to be by order of accretion event, by chronological order of accretion event, but by chronological order of discovery. And the first tidally disrupted galaxy that has been discovered was this one right here. This is the Sagittarius dwarf spheroidal galaxy. So straight up from the discovery back in 1994, I'm going to go like to this side. Back in 1994, before I was even born, actually, this galaxy, just from looking at the isophotos of this galaxy, you could already see that this thing was really, really distorted and probably ongoing tidal disruption, because this thing is really close to the galactic center, like something like 20 kiloparsec away. From the perspective of the sun, this galaxy, although it's like relatively massive, it's almost this mass of the SMC, it is like from the perspective of the sun, behind the galactic disk and behind the galactic bulge. So this is why it was very difficult for us to discover this galaxy in the first place. And then eventually, with the advent of all-sky photometric surveys, specifically for this one system, the advent of 2MASS, we were able to just map out the entire tidal tails of this galaxy throughout the whole sky. So this is really a magnificent tidal tail around this one galaxy, what we call these elongated structures we call stellar strings. And just a spoiler from my thesis, back a few years ago, like actually 2 years ago or something, I started working on this project on the Sagittarius string. And this stellar string actually has been known for quite some time that this thing has 2 distinct chemodynamical populations. One is more metal poor and more dynamically hot, and the other is metal rich and dynamically cold. And we were able to use actually this exact N-body model that I'm showing right here, use this N-body model combined with other techniques to show that these different chemodynamical populations in the string were actually the result of the fact that this galaxy, before undergoing tidal disruption, had already developed a metallicity gradient. And again, like going back from the title of the talk, like from the perspective of galaxy evolution, I think this is really important because this shows us that these dwarf galaxies at the mass of Sagittarius can develop these metallicity gradients really quick. And then moving on, then after, with the advent of Hipparchus, this Hipparchus is one, ancient to me right now. This astrometric mission, this is very close to the sun. So basically stars that were 100 parsec away from the sun. People were able to use astrometry from Hipparchus to calculate motions of stars around the Milky Way, around the sun, and specifically by doing this for stars that were low metallicity, metal poor stars around the sun, people were able to use the motions of stars, specifically the angular momentum vectors of stars, to find this thing that we call the Helm strings nowadays. And specifically, this one string was found because the angular momentum vectors of stars that are members of this string were very different from the bulk of the stellar halo around the sun. Why I think this is interesting to mention is that I also had a paper on this. Specifically, we looked in a previous paper at the chemical compositions of stars in this one dwarf galaxy. And you can imagine that star formation in this tidally disrupted dwarf galaxies, it quenches very quickly at the time of accretion. But specifically, from the chemical abundances of this one galaxy, we were able to show that this one galaxy specifically experienced at least 2 bursts of star formation. So instead of having a simple star formation history with a single burst, this one galaxy, from the chemical compositions of stars, this one galaxy at least experienced 2 star formation bursts, which I think it is, again, very important because this is probably similar to what happens with the LMC and the SMC from the perspective of galaxy evolution in general. Moving on, then we go into the SDSS era with like 2 new discoveries like this orphan string and this Sirius string, which are in red and green right here. I don't have papers on this, but I have incoming observations next week with Magellan telescopes to obtain, again, detailed chemical compositions of stars, and I think it's really important that we can actually do. And note that the trend right here is that we can use these disrupted dwarf galaxies, and the reason we can use them to learn about galaxy evolution is because these stars just belong to the Milky Way. So they are nearby, they are close enough for us to get very detailed data for this thing. So we can do, for instance, high-resolution spectroscopy to derive detailed chemical compositions for stars in these things and learn about galaxy evolution in this regime, which otherwise would only be accessible with galaxies that are 100 kiloparsec away. And then moving on now into the Gaia era, which is what everyone loves, we had one major discovery right at the beginning of Gaia DR2, which was this one thing that is called Gaia Sausage Enceladus. You will see that people give funny names to these things. This Gaia Sausage Enceladus is a galaxy that was really a major galaxy that has merged with the Milky Way probably 10 billion years ago. This galaxy was maybe the same size of the LMC. So this really was like the last major merger that has been experienced by the Milky Way. And one of the things that I think is really important about this is not only because we are like discovering one major event in the history of the Milky Way. So from the perspective of the evolution of the Milky Way itself, this is very important because this should have several implications to the overall evolution of our galaxy. I think it is really cool that we are able, again, to use this system to learn about something about galaxy evolution. In this paper, what we did was to look not only at the stellar populations of this dwarf galaxy, of the disrupted dwarf galaxy, we were also ended up like looking at the population of globular clusters associated with this galaxy. So as you can imagine, not only we have stars in the halo, but we also have globular clusters. And these globular clusters are also brought in with these accretion events. And specifically, what we were able to identify is that this one galaxy, this Gaia Sausage Enceladus, for many reasons that I'm going to go in detail in the next slides, is probably associated with ωCentauri. And ωCentauri is important on its own because it's the most massive globular cluster in the Milky Way. And we have known for quite some time that it's probably not a regular globular cluster, not a classical globular cluster, but rather the nuclear star cluster of a stripped dwarf galaxy. And well, this is the dwarf galaxy that brought in ωCentauri. And this is not just a curiosity. I will show you guys how this can have implications to what we know about a bunch of things in galaxy evolution. And then this is one of the most recent discoveries, this Wukong stellar string, again, funny names. Another trend that you can see is every time that we have new data, like we went from 2MASS, to Hipparcus, to SDSS, and then to Gaia, every time that we just have new data, we just find more of these things. And you can imagine the bunch of these stellar strings that we are going to find in the LSST era. And then what I think it is important about this is that in a paper that I published earlier this year, we were able to use the chemical compositions, again, the detailed chemical compositions of stars in this one stellar string to argue that this ended up, like, although in the form of a stellar string, this ended up being the first example of a dwarf galaxy that has been chemically enriched in very heavy elements, like those elements that are created in neutron capture, in the neutron capture process. This galaxy was enriched in these very heavy elements through neutron star mergers. So this ended up being the first example of a galaxy that has been predominantly chemically enriched in these elements through neutron star mergers, which you can imagine is important for a bunch of different reasons. So, and then one of the most recent discoveries was this one stellar string right here associated with this one galaxy that we call Crater 2. This is going to be the topic of the second part of my talk. This one dwarf galaxy right here, I think it is really interesting because this one galaxy is probably the faintest galaxy from the perspective of the surface brightness that we know in general. So this galaxy has a surface brightness that is like 5 magnitudes fainter than what we call ultra-diffuse galaxies. So this really is an extreme analog of what we call ultra-diffuse galaxies in extragalactic environments. And this thing is tidally stripping. So this is the stripping model that I calculated from a paper that I'm writing, hopefully, eventually. The tidal stripping model that I calculated for this system, and this is the string that it produces. So all of this is to say that basically, the message that I'm trying to convey is that we can not only, these accretion events, this sequence of accretion events not only are important because they are crucial to the evolution of the Milky Way itself, because this is telling us about what is the accretion history of our galaxy, but also they are important on their own because we can learn about galaxy evolution on a star-by-star basis by looking at, for example, the detailed chemical compositions of stars, simply because they are so close to us that we can just go out there and get high-resolution spectroscopy to get detailed chemical abundances, for instance, for these things, and also detailed kinematics for these things. And so they are important on their own because we are actually going into this regime of this of detailed evolution of these dwarf galaxies. Basically, to summarize, right here I'm showing on the left. This is a simulation on the left. This is a simulation that is from the Aquarius project. This is a cosmological simulation. This is showing the halo of a Milky Way mass galaxy, or a Milky Way analog in the simulation. And this is showing the halo of this Milky Way analog color-coded. So every particle in the simulation is colored by the different progenitor systems of these particles. So every single color right here is a different dwarf galaxy that has been accreted in the simulation. So basically what we can do right now, thanks to Gaia and other spectroscopic surveys, is to really use this data to kind of color code, just like in the simulation, to color code the stars in the halo of our galaxy in order for us to really reconstruct what is the detailed accretion history of the Milky Way. And this is important not only from the perspective of the Milky Way, but also from the perspective of learning about galaxy evolution. And so, moving on, I just wanted to show how this really works. So in practice, what we do, I mentioned those Helmi strings that people use angular momentum to identify which stars were members of that thing, and in order to distinguish from the bulk of the halo of our galaxy. So this is exactly what is shown in this movie. So on the left panel, this is just spatial positions. What the left panel is doing is just throwing simulated dwarf galaxies. This is just a very simple any-body simulation, throwing into a gravitational potential that is supposed to replicate the gravitational potential of the Milky Way. And this is a static potential. I don't even have a bar. I don't even have spiral arms. And even so, you can see that what happens over time is that you produce these elongated structures that is producing right now. So these elongated structures that I refer to as stellar strings. And over time, these things get what we call phase mixed with the halo of a galaxy, and they will eventually become just part of the smooth and isotropic stellar halo. However, on the right, what I'm showing is in the vertical axis, I'm showing the total energy of those particles. So this is the total orbital energy, so the sum of kinetic and potential energy. And in the horizontal axis, what I'm showing is this z component of angular momentum. For many reasons, this z component of angular momentum is conserved. And you can imagine that because the Milky Way has a disk, it's not spherical symmetry anymore, so angular momentums in general are not conserved. This z component specifically it is. So we can use the orbital energy that is conserved and also this z component of angular momentum to just group together or cluster together with dynamics stars that belong to the same progenitor system. So when you really see things that are clustering in this space that we call integrals of motion space, because these things are conserved, we can just argue that these things came in with the same accreted dwarf galaxy. Okay, so just like I said in the introduction, we can not only do this with stars, we can do this with globular clusters. So this now is jumping straight into the actual talk. Oh, actually no, that was this extra slide. So this is the situation, sorry. And the situation right now is kind of chaotic. People have argued for a bunch of substructures. This is the same energy and angular momentum space. This is energy, sorry, this is my mistake. Basically, this is separated into two panels just because for us to, for better visualization. And then I have marked right here with check marks the things that are real and that are relevant. For instance, this GES is that Gaia sausage, the last major merger of the Milky Way. And with question marks are the things that I don't think are irrelevant, but I think that are like, we don't know if they are real in the sense that we don't know if they are part of some larger structure. For instance, this one right here, again, funny names to these things, but this one right here, we don't know if this is just a part of this larger one thing right here, that is the Gaia sausage thing. And with axis, I'm marking things that are irrelevant for this talk because they are formed in situ, so they are part of the Milky Way itself. And so this is basically the situation. We have a bunch of like these disrupted dwarf galaxies or this proposed disrupted dwarf galaxies that we have uncovered using this data from Gaia and by doing this clustering in dynamical space. But we can not only do this with stars, we can do this with globular clusters. So here it is. And this is what we have done in that previous paper that I mentioned about the Gaia sausage Enceladus that we published. So this is the same energy and angular momentum space. However, this is for globular clusters. These are galactic globular clusters. And in blue, I am plotting in blue all of the globular clusters that are dynamically associated with this last major merger. And what we can see is that this one event brought a bunch of globular clusters. You can imagine if you are used to this, there is a relationship between the total mass of a galaxy and the number of globular clusters. So you can imagine that this thing to have like 20, maybe 30 globular clusters, it has to be really a pretty massive merger event. However, not only have regular globular clusters that are dynamically associated with this thing, we also have ωCentauri. And this is the main thing. ωCentauri is dynamically associated with this Gaia sausage Enceladus sphinx. However, these associations are not unanimous in the literature. There are some people that argue this ωCentauri because this orbit is very retrograde, as you can see right here. On the right, we have retrograde things. On the left are prograde things, moving with the disk. And this ωCentauri has been argued to be part not of Gaia sausage, but of other accreted substructure, whatever. What matters is that this association is not unanimous. And there are people that have even proposed that other globular clusters, like this NGC 1851, should be the nuclear star cluster of this galaxy. And then here we go on a journey to show that this is not the case. First, because from the perspective of dynamics, if you have something that comes with the core of an accreted dwarf galaxy, it should sink deeper into the potential. Basically, it should get to lower energies. So if this one thing is a nuclear, is your star cluster is a nuclear star cluster, it should be in the center of the galaxy, literally the spatial center of the galaxy. And because of that, it should be the one thing with the lowest energy out of all of the other clusters. This is exactly the case for ωCentauri. And this is not the case for NGC 1851. So from the perspective of dynamics, I don't think there's any reason for you to call this the nuclear star cluster. And this is exactly showing this. So this is a chemodynamical simulation of this last major merger. So this is the galaxy that develops in the simulation, and it's color-coded by the metallicity of the particles in the simulation. And in red, you can see that are the more metal-rich things that develop in the center. And when this thing merges with the Milky Way, it becomes this in this energy angular momentum space again. And you can see that the things that are more metal-rich, that are red, end up sinking deeper into the potential because they are in the center of the galaxy. So from the perspective of dynamics, we think that ωCentauri should be the nuclear star cluster. And then this is the thing that really really shows you that this NGC 1851 or any other globular clusters associated with ωCentauri or associated with Gaia sausage should not be the nuclear star clusters, and it's because of chemistry. So what I'm showing here in the vertical axis is the metallicity dispersion of your globular clusters. And if you have been to your stellar evolution classes or like stellar population classes, whatever, you know that globular clusters are prototypes of simple stellar populations. So they should really have the same, all of the stars should have the same exact chemistry. They should have exact the same metallicities. And this is not the case. Right here, we have things that have very low metallicity dispersion. So they have different metallicities, but by a tiny bit. And this is basically within the uncertainties that we have in these metallicities. However, this is not the thing for ωCentauri. ωCentauri really has a humongous metallicity dispersion that is typical of what you expect for nuclear star clusters. So there we go. And then the thing that really is the nail in the coffin for me is this plot. So this plot is showing on the horizontal axis, the stellar mass of host galaxies of nuclear star clusters, and the mass of nuclear star clusters is in the vertical axis. Basically, if you just check what is the expected stellar mass of the host galaxy of ωCentauri, you end up with this green line, and this green line crosses this relationship exactly at the location of Gaia sausage. So, but the most important thing is not this, because this could be a coincidence, right? The most important thing is that all of the other accretion events that happen in the history of the Milky Way that we know of, that I showed in the previous slides, they really are 100 times less massive than Gaia sausage. So they basically occupy this region in this axis of stellar mass of the host galaxy. So if you invoke that because if some other galaxy was the host galaxy of ωCentauri, it really would be like an extreme outlier in this relation. So this is the situation. And I think this is how you approach this. You really have to invert the question. The question is not what is the nuclear star cluster of this Gaia sausage thing, this last major merger, but really what is the host galaxy of ωCentauri? Because ωCentauri we know for sure is a nuclear star cluster. And I don't know, from the arguments that I have presented, I think ωCentauri, Gaia sausage, which is the star right here, this last major merger, this Gaia sausage thing, is the best candidate that we have to be the host galaxy of ωCentauri. Okay, so, but this is a paper from 2 years ago. Now we have new things, because people have discovered, actually, an intermediate mass black hole inside ωCentauri. So this is a result that was published like a few months ago. So a few months ago, people published this data. So on the left is just a spatial distribution on the sky of stars in gray that have high quality proper motions from Hubble. So this is the central region of ωCentauri with a humongous baseline of like 20 years from Hubble, and also with like more than 500 exposures. And then by taking a look at the stars that have high quality proper motions in this data set, we can look in this more, this central, the innermost regions of the cluster for those stars that have very high velocities. So this is plotting right here to the right in this paper from like this year, from a few months ago, is stars that are in the core of ωCentauri but have very high velocities. So they have very high tangential velocities above what you would expect from the regular escape velocity of the cluster. So really, I don't know, I'm not the person arguing this, but what they argue in this paper is that the best explanation for this is to invoke that this ωCentauri thing really hosts an intermediate mass black hole. So an intermediate mass black hole at about 10,000 solar masses, and with the minimum mass of like 4,000 solar masses and an upper limit of 20,000 solar masses. So really in that regime that we call intermediate mass black holes. However, I have just presented for like the last 10 minutes that ωCentauri is our nuclear star cluster, and the nuclear star cluster and the host galaxy of this cluster was Gaia sausage, the last major merger. So we can tie those two things together to actually learn something about galaxy evolution. And this is how we do this. So this plot is very busy, but I'm going to walk you through the things that matter. In the horizontal axis, we have stellar mass. So this is the stellar mass of the host galaxy of these central black holes. And in the vertical axis, we have the mass of the black holes, the central black holes themselves. And basically, this black line is, I mean, one of the most recent determinations of this relationship between stellar mass and central black hole mass. But this relationship is really derived from only massive galaxies, from galaxies that have stellar masses above 10 to the 10. So really massive galaxies. So the Milky Way, for instance, is right here. And this line is derived for these galaxies right here in blue and gray. However, if you just extrapolate this one relationship that is derived for massive galaxies to the regime of dwarf galaxies, what we find is that this relation really just goes right on top of this central black hole of ωCentauri, so the central black hole of Gaia sausage. So why I think you should care about this, instead of just being some curiosity, is this has several implications, not only to the formation of this black hole, because now we know that this black hole is forming inside this one galaxy that is kind of LMC mass galaxy, but also it's forming a nuclear star cluster. And this could have implications to the seeding mechanism for this central black hole. But also what happens is that now that we know that galaxies like the LMC could host black holes that are this massive, we could really try to ask what is the dynamical impact in the evolution of LMC mass galaxies with the presence of these black holes that have this mass ratio with stellar mass. And then what I think is more important is that this black hole really has a very low mass. 10,000 solar masses is really low mass if you think black holes form from direct collapse. If you think that your black holes are forming from direct collapse, what should happen is that you would have like this distribution right here of initial masses. So this distribution in blue. Basically, you know that the vertical axis is in log scale. So basically what this distribution means is that it's very difficult for you to produce a black hole that has 10 to the 4 solar masses of initial mass. However, what I think it is interesting is that if you, instead invoking of the traditional direct collapse black holes, so traditional heavy seeds, if you invoke formation of central black holes with this mechanism that is called runaway stellar mergers. So in this scenario, I'm not the one proposing this, but in this scenario, what happens is that if you have a galaxy that is forming a nuclear star cluster, what can happen is that you can have just a bunch of stellar mergers in the nuclear region of the galaxy, and this could produce a central massive black hole. And the central black holes that are produced with this mechanism have lower masses than the direct collapse scenario. So this could be one explanation to the low mass of this globular, of this central black hole, because we know that this one central black hole is indeed inside a nuclear star cluster. But then another thing that is interesting is that this black hole has such a low mass that is very difficult, actually. I mean, this is very simple calculations that I made, but it is very difficult for you to explain the mass of this black hole with direct collapse. Because if you produce something with direct collapse, which has like 10 to the 4 solar masses, in this case, I'm initiating this calculation in orange with a heavy seed of 8,000 solar masses. And if you accrete at only 1% agiton rate, you would have like this evolution line right here. So basically, this means that if you have heavy seeds as the formation mechanism for all central black holes, what would happen is that this one black hole right here inside ωCentauri should have a very, very quiet accretion rate. Over the whole 3 billion years until the accretion by the Milky Way of Gaia, Sausage, and Enceladus, this central black hole should have a very quiet accretion history. And why I thought this was interesting at the time meaning 2 months ago, is because just recently I have been to this conference when people were talking a lot about these galaxies right here. These are galaxies at very, very high redshift, as you can see right here. For instance, there is this one example, GNZ11, that has a redshift at more than 10, which has a very massive black hole, a very high mass black hole. And in order for you to explain these overmassive black holes at high redshift, what you really need is the complete opposite of ωCentauri. What you need is a very heavy seed and very high accretion rate, like sometimes above Eddington rate, which is very difficult to imagine. So if you invoke that heavy seeds are the sources of all central black holes that exist in the universe, what you have to say is that this one central black hole inside ωCentauri has to be the complete opposite history of accretion history than these overmassive black holes that are detected with JWST, for instance, GNZ11 right here. Anyway, so this is kind of the bottom line. I think this was really cool result. I have submitted this paper, and I'm really going to stop right here. Oh, sorry. I'm really going to stop right here to ask if you guys have any questions, and then I can move on to the next part of the talk. Lerch?
Is there any X-ray emission in ωCentauri from this black hole?
I don't think there's any X-ray emission detected. But for instance, what I know is that people, I don't know how is the situation right now, but what I know is that Ranieri, that was a PhD student here, he was looking at Fermi data, and there is some gamma ray emission from the center of ωCentauri. So I don't know, this could be related, but I'm only thinking now about this just because you asked, but I don't know if there's any X-ray detection specifically. So that's it. Okay, so we can come back to this anyway, by the end of the talk. And now I want to move on to another result that I have to write the paper still. But this other result is, again, about disrupted dwarf galaxies. But this one was about a fully disrupted dwarf galaxy. So this thing, we don't even see the galaxy anymore. It's just completely, fully disrupted in the halo of our galaxy. And now I want to move on to a galaxy that maybe exists, and it is tidally disrupting right now. So this galaxy right here is called Crater 2, which is the galaxy that people say does not exist because this is the central region of the galaxy, and there is nothing there. And there's nothing there because this galaxy really is extremely, extremely diffuse. The ultra-diffuse terminology is already taken, but this galaxy is really a lot more diffuse than ultra-diffuse galaxies. So ultra-diffuse galaxies are defined as those galaxies that are these galaxies right here that have central surface brightness of something like 25 magnitudes per arcsecond square. And the central surface brightness of this galaxy is something along the lines of 30 magnitudes per arcsecond square. So this thing really is an extreme again, analog of these ultra-diffuse galaxies. And we know that there is a galaxy right here because we just see clumping in proper motion, for instance. And we also see color magnitude diagrams, variable stars like Aralita stars, and all of those stuff. And then, but this galaxy is so diffuse to the level that people have claimed that this one galaxy is a problem for lambda CDM. In the sense that you just cannot explain how you produce such a faint galaxy, such a low density galaxy with lambda CDM if your galaxy is isolated. However, lambda CDM actually provides you with a mechanism that could produce these very diffuse galaxies, which is tidal stripping. So tidal disruption should be capable of enlarging galaxies. However, this galaxy is diffuse enough that you need to invoke that this galaxy has lost 99.9% of its total stellar mass to explain its size. 100 kiloparsec, 110 kiloparsec. Or you can invoke that your dark matter halo, instead of a traditional Navarro-Franken-White cuspy halo, is a core halo. So this is why this galaxy is interesting, because you need to claim core halo in order to explain its size. And just to have a notion of how big this galaxy is approximately 1,000 times less massive than the SMC, but it has the same size on the sky as the SMC. So this is really a humongous galaxy. And you can see that this galaxy crater 2 is not alone. There are other galaxies in the local group, for instance, this one right here, which is an Andromeda satellite, and this Antillia 2. This surface brightness is actually being revised to the level of crater 2. All of these galaxies are these super extremely diffuse galaxies in the local group. And then, just for the sake of comparison, this is the Milky Way. Like, this is just for illustration, okay? This is the size of the LMC on the sky, and this is the size of Antillia 2. And this is not exactly the same comparison, but I mentioned that crater 2 is 1,000 times less massive than the SMC, and Antillia 2 is 1,000 times less massive than LMC. So really these things are crazy faint. So they are so diffuse that they are 1,000 times less massive than the Magellanic Clouds, but they have the same size. So what can we do with this? So I just mentioned that tidal stripping is the natural explanation for, or might be part of the explanation for the sizes of these galaxies. So it's very important that we confirm that these things are tidally disrupting. And so what I did is I am part of this collaboration that is called S5. S5 stands for, here we go, Southern Stellar String Spectroscopic Survey. And what this survey does is to really do spectroscopy of anything that is tidally disrupting in the southern sky. So this is one footprint from a paper that was published, I think, in 2022. Yeah. So as you can see, we have this footprint that is really a bunch of like these straight lines, these elongated things, which are to trace the elongated structures of stellar strings. So basically, we just go after everything that is tidally disrupting, and we do low-resolution spectroscopy with an instrument that is called 2DF on the Anglo-Australian telescope, which is a 40-meter telescope. My battery is going down. But basically, we do this, and we get low-resolution spectroscopy to get radial velocities and metallicities for stars in these systems. And then, this is basically the main plot, just to show basically everything. And this is also a very complex plot, but I'm going to walk you through this again on the things that matter. So this is the footprint that we have, these large circles right here. These are really, as you can see, these are really humongous field of view from this instrument. And it really is why we use this instrument is because this has this huge field of view. So we can cover large areas along these strings. And then we are covering around the center of the galaxy, which is plotted here in orange. We are covering this string track that is predicted from the orbit of this galaxy. So basically what we do, we run the orbital history of this galaxy using Gaia proper motions combined with our radial velocities. And then we have something like what should be the orbital history of this galaxy. And then in our simulation, we just, instead of actually doing a full any-body simulation, what we do is just we integrate the orbit of this galaxy. And then what we do is this strategy that instead of doing the full any-body, we just launch swarms of particles, kind of like swarms of any-body particles from the Lagrange points during the orbital reconstruction of the system, and we have this string track that is predicted. And then, using like some like mixture model kind of thing, what we do is we find these members in green. So we really can see that instead of having a bunch of members around the center of the galaxy, so this galaxy really does not have an extended halo. This galaxy really has a stellar string. So it has a bunch of like these green points right here along the string track that we predict. So this galaxy really is apparently undergoing tidal disruption. One thing that I think is interesting is that this figure right here, the model in the background, is color-coded by the distance of the particles in the simulation. And what you can see is that there is a part of the string that is like close to us, which is the blue points, and a part that is far from us, which are the red points right here. And if we plot on top of this, a bunch of RR LiDARs from another survey that covered this area, if we plot all of the RR LiDARs, they are actually following this distance gradient. These are the symbols right here with black edges. They are color-coded again from the distances, and we can see that following what we expect from the model, we have a distance gradient. So these are the near side of the string. We have actually RLidas that are close to us, and right here we have RLidas that are far from us. Let me solve this. Obrigado. Obrigado. Pronto. Agora estamos bonito. So, moving on. This is the simulation that we have. So this is the stripping model simulation that I just described to you guys. And what I think it is really fun, and this is just curiosity, okay, guys? What is curious about the simulation is that if we run it with the LMC, we get the red track, and if we run this with the LMC or without the LMC, we get the blue track. And the reason for this is not because the LMC is perturbing the orbital history of this galaxy, because this galaxy really is very far away from LMC. It doesn't even get close to the LMC. But what is happening is that in the interaction between the LMC in red right here and the Milky Way in blue right here, what happens is because the LMC is so massive, the LMC and the Milky Way are really orbiting the semi-barycenter instead of the LMC orbiting the Milky Way. So what happens is that the LMC really pulls the Milky Way out of the original center, and is now the Milky Way is now moving towards the LMC at approximately 40 kilometers per second or something. So the LMC is displacing the whole Milky Way, and this is why these models differ. Is because one of them is just more closer to us because the Milky Way is actually moving. This is just a curiosity. And then this is the actual result that matters for people that care about the dynamical evolution of these ultra, extremely diffuse, super diffuse galaxies. This is what we derive from our data. This is a velocity gradient. So what we found was that if we cover the entire footprint of our survey, what we find is this velocity gradient. So not only there is a distance gradient that we found from the RLidas that were covering this area, which is right here, we also have this velocity gradient, which is exactly what you expect from tidal stripping. Basically, some stars are in front of the orbit and some stars are behind the orbit, so they have some velocity difference because some stars are just, in the case of this galaxy, some stars are just past apocenter and some galaxies are still reaching apocenter. So this is basically what happens, and this is exactly what you expect from tidal disruption, is to find these velocity gradients because the string really is accelerating from one point to the other. Okay, so not only I mentioned that not only we measure radial velocities, but we also measure metallicities. So this is where I wanted to get. It is to this figure. So this is, again, this is, as you can see, I make very confusing figures, but I'll walk you through this again. So this is the mass metallicity relation for dwarf galaxies in the local group. Well, this is not the mass metallicity relation because in the horizontal axis I'm plotting the absolute magnitude in the V band, but I have some correspondence with stellar mass assuming some mass-to-light ratio on the top, and then we have metallicities in the vertical axis. What I think is interesting is that this galaxy right here is below this mass metallicity relation, which is very weird actually. Because if you think about it, if this galaxy has really experienced a lot of tidal stripping as we expect to explain its humongous size and also what we expect because we see a stellar string attached to this galaxy, what you would expect is that a galaxy that is born on top of this relation should really move to the opposite direction. It should move this direction because this direction is the direction of low mass galaxies, and if you're losing mass, you should show up as a low mass galaxy when you were really born as a high mass galaxy, which is exactly what is happening to Sagittarius right here. So Sagittarius I show in the first slide of the talk that has this gigantic stellar string and has lost a lot of mass. And this galaxy really is an outlier in the mass metallicity relation, but it's on top of the relation. It has a higher metallicity to its present day mass. But this is the contrary that happens to this crater too. If we compensate for mass loss that we expect to have happen, if we compensate for like 50%, then 90, then 99% mass loss, this would become 2 sigma, then 3 sigma, then something like 6 sigma outlier in this relation. So this is something that got me really interested in this because it got me really thinking. So this is now me speculating. This paper is not submitted yet, not published. This is me speculating. What really controls this mass metallicity relation is really just regular like baryon cycling within a galaxy. So if you think about a galaxy that is evolving within this dashed red line, you have like some inflows that in, for instance, galaxy like those gas regulator models that we learn like in grad school, you have like some inflow of gas, some accretion rate of gas into your system, into your galaxy, And this can be controlled in these gas regulator models that we learned in high school, not in high school, like in grad school. This could be controlled by the cosmological merger trees or something. And then we have all your star formation happening, and out of your star formation, you have some supernova that are exploding. Some of the metals that are produced go back into the cycle. They are retained within the galaxy, and this is what is shown in this term right here. This R times the star formation rate. This R is the return fraction of gas into the system. This we learn in chemical evolution. This is the discipline. And then you have like some fraction of gas that is expelled out of the system in the form of outflows, in supernova outflows. And the amount of gas that is expelled is really controlled by this term right here that we call the mass loading factor. And this is basically what controls this relation. You can imagine that low mass galaxies, they have lower metallicity, not because they are creating less supernova, because for a given stellar mass, you produce the same amount of supernova. But they really have low metallicities because they are losing all of their metals to outflows. So they don't have deep enough gravitational potential wells to retain those metals. And then what happens is that this relationship right here, this mass metallicity relation, some people propose that it might not be, the metallicity might not be intrinsically connected to the stellar mass, but really to the gravitational potential, so the total mass of the galaxy. So then what we can do is, you can imagine that this relation should really be a relationship between stellar mass and not your, relationship, sorry, with your metallicity, and not with your, really your stellar mass, but really something that is a proxy for your gravitational potential, such as the density of the galaxy or something. And then people have proposed this figure right here. People meaning some people that do this extragalactic stuff, but this is me proposing this for the local group, I guess. This is the mass metallicity relation again, but instead of the stellar mass on the horizontal axis, what I'm plotting right here is the ratio between stellar mass and the half-life radius. So this is the ratio between the stellar mass and the size of the galaxy, and this should be a better proxy for the gravitational potential. And as you can see now in this figure, this galaxy is no longer an outlier. And even if you compensate for this mass loss that this galaxy has experienced, note that this thing right here in the horizontal axis goes with the log scale. So if this goes with the log scale, you need to really lose like 99% stellar mass loss for you to really come like something like here. So this wouldn't be really even be like a big outlier. So maybe what is happening is that this galaxy really is very low metallicity because it was not capable of retaining all of the metals that it produced. And maybe this could be because this galaxy really lost a lot of its dark matter mass very early. And why very early is because of this figure. So this is the color magnitude diagram of this galaxy. So this is the final thing to close everything. As you can see, there are two sequences in this color magnitude diagram. And these two sequences indicate, I mean, if you go to like, I don't know, intro to astronomy as undergrad, you learn that like this difference in the CMD should really be associated with the difference in the age of these stellar populations. So, but the youngest stellar population that there is in this galaxy is 10 billion years old. So the younger population right here in blue is 10 billion years old. So this galaxy really stopped forming stars very early on, so a long time ago. So what could be happening to this galaxy is that this galaxy had some encounter with a massive host. Don't know if the Milky Way, don't know if this is pre-processing. But this galaxy could have experienced some encounter with a massive host that stripped this galaxy out of its dark matter mass, out of its dark matter halo. And then eventually when it was forming all of these stars right here, it then stopped forming stars because it was stripped all of this gas also. But basically you lost all of the metals that you produced right here. So this is what causes this galaxy to have a very low metallicity, but to be consistent with this relationship, not only with the stellar mass, but also with the size. So I think this is it, what I wanted to talk about, and I'll leave you with some conclusions. I think basically the takeaway message is that we can learn a lot about galactic evolution by looking at these tidally disrupting galaxies. And not only we can learn about the accretion, but we can learn about galaxy evolution by looking at the individual systems themselves. So that's it. I'll be happy to answer any questions. Gaston?
Hello. Yeah, nice talk. Thank you very much. It was very interesting. I have a curiosity about ωCentauri. Does it have a dark matter halo?
not to the best of our knowledge. So people have tried to, this is basically one of the reasons why people have 500 exposures with Hubble into this cluster. One of the reasons is to check if it has some remaining dark matter, and I think they were never conclusive. So basically the data does not require dark matter.
Okay.
But maybe if you get, instead of 20 years of baseline, maybe we have 50 years, we're going to have something.
Okay. And about the Crater 2 galaxy, does it has, can you measure the rotation of it? Does it have some measurable spin?
It apparently does not have any rotation. However, you can measure the velocity dispersion. And the velocity dispersion really supports the scenario where this galaxy just lost a bunch of its dark matter halo. So the halo to stellar mass ratio of this galaxy is like 30. And it really should be like 1,000 for this stellar mass. So it really has lost basically all of its stellar halo, but it's still there. We can measure, we can resolve velocity dispersions in this, yes.
Okay, thank you.
Very nice talk, Guilherme. To have globular clusters?
No, it does not. But I don't think it is unexpected, because if out of the Milky Way satellites, like the one that has an anomalous number of globular clusters is like Fornax dwarf spheroidal. And this galaxy is like 100 times less massive than Fornax. Maybe not 100 times, maybe like 50 times less massive. And Fornax is already kind of an outlier. So galaxies at the size of Fornax, they have a number of globular clusters that's on average like 1 plus or minus 10, so because of the uncertainties in this relation.
Mm-hmm.
So it's not unexpected that this galaxy does not have any globular clusters.
Mm-hmm.
Originally, people thought that this galaxy had infall with the Crater 1 globular cluster. It's a globular cluster that is in the constellation of Crater. And it has apparently experienced like grouping fall with some other galaxies from Leo constellation. But Crater 2 has been shown recently, like not even 6 months ago, to not be part of this grouping fall. So I don't think there's any evidence for a globular cluster in it.
Do you know whether there is some study trying to put constraints of dark matter particles using this sort of streams?
Yes, a lot. So specifically what people do, specifically for Crater 2, people just try to model the whole thing. People try to look at very, very ultra high resolution simulations of like Milky Way zoom ins. And they find things that are similar to Crater 2, but not quite. But what people really do with strings is, let me go to this figure. What people really do with strings is to look at perturbations in strings. So this right here, there's an example. You can see that there are some orange points right here, which is referring to this Pauka string. And there's like these red points right here, which are associated with this AAU thing. I don't know, I think, yeah, I don't know, something like this. But these red points and this green and these red points and these orange points, they are 2 strings originally, but people have realized actually from this survey, people have realized that they just have very consistent radial velocities, so they are just on a same radial velocity gradient, on a same distance gradient from like blue horizontal branch stars. So what people believe is that this string specifically, but others as well, they have this perturbation. They are 2 strings in the sky because they were perturbed by something. And people believe that it could be dark matter subhalos. So people use these perturbations in strings to calculate what is the amount of mass that you need to create that perturbation. And then if you don't have anything that has an orbit that is even similar to the orbit, to the impact parameter that you need to create that gap, like you don't have any close encounter with any globular cluster, no close encounter with any dwarf galaxy that you know of, you then try to speculate kind of that it could be an encounter with a dark matter subhalo. So then people can put like lower limit to the minimum subhalo dark matter, like the lower limit to the minimum mass of the dark matter subhalos. So people find things like 10 to the 6 solar masses for the minimum mass of the subhalo. But this is very, my view is that this is kind of like very speculative, because you really need to invoke that the impact has to be with a dark matter subhalo, which I think it is difficult to, it is very difficult for you to say that this is the case, basically. But this would have implications to particle physics.
What about the Magellanic Cloud? Do you think that is in the first encounter with the Milky Way, or it has passed already many times?
Probably from the simulations that people make, it's on first infall. So this is one of the major things that has been kind of like not consolidated with Gaia, yes, but not discovered with Gaia, is that Magellanic Clouds are probably on first infall. So this is consistent with this reflex motion that we find in the halo of our galaxy. This is consistent with some perturbations in some stellar strings. That is specifically this one stellar string, that is this one right here in purple, which should be right here. So this one in purple is one string that is very, very sensitive to the perturbation of the LMC. And if it's not on first infall, it would really be difficult to explain all of these things at once. The perturbations that we see in the halo, for instance, the encounter with the LMC cause like basically disturbs kind of like the dark matter halo, and it also disturbs the stellar halo. So you can map out these disturbances, these perturbations, but you can also map out perturbations in stellar strings that are clearly caused by the LMC. And if you do not assume first infall, then we don't know just how to explain all of these perturbations at once. So yes, it's probably on first infall, and from stellar strings, you really consolidate that scenario.
Great talk. About the crater 2, you said that one of the hypotheses is that this galaxy lost its dark matter halo. In that case, this galaxy had to go pass through a larger dark matter halo before in its history.
Yeah.
And so what about the baryonic counterpart when this happened? Isn't it possible that you track this somehow? I don't know.
Yeah, I mean, this is one of the reasons why we want to track the stellar string, right? So one of the things that would put a lot of constraints on what you're asking, which is, just tell me if I understand it right, this would be to tell how much stellar mass has been lost. One of the ways to do this is to cover the whole footprint of the string, which is impossible with spectroscopy. Like, it's the string track that I calculate covers like, I don't know, like thousands of degrees on the sky. I don't know, like a humongous area, like the whole sky basically. However, one thing that you could do is to track this with photometric surveys. So this has a very low, like, I mean, the galaxy itself is so diffuse. So imagine tracking the surface brightness variations of the stellar string. This would be impossible. What you can do is to use something like narrow band surveys. Like this is the thing that I talked about in S+. You can do this with narrow band surveys, because if you have some metallicity sensitive photometry, you could really try to select along the string track those stars that are very metal poor, because this galaxy is just very, very metal poor. As you can see right here, it's like at a metallicity of -2 in F1H, which is like not very common. So the stars at -2 are very rare. So you can really distinguish along the string track if your stars are associated with the string, because not only you have the metallicities from photometry in this case, but you also have Gaia proper motions. So you could do the same thing that I did right here in order to find the members, which was to do like some kind of fancy mixture modeling kind of thing. But you would lose the rate of velocity information, but you would have the metallicity information plus the proper motion information for you to calculate the total mass loss, the stellar mass loss. However, in general, what happens to these galaxies in anybody's in simulations is what happens, for instance, to Sagittarius. One of the key things in my paper from Sagittarius is that when Sagittarius experiences its first encounter with the Milky Way, it loses like 50% of its total mass, so 50% of its mass in this dark matter mass, and basically loses nothing of stars. Basically loses like 1% of its stellar mass. And it really is in the second encounter that Sagittarius starts losing a lot of stellar mass. So in the second encounter, Sagittarius lost like 50% of the stellar mass straight away. So basically what happens in these things is that when you have your first encounter, your first what we call pericentric passage, which is your close encounter with the massive host, you basically lose your dark matter. And the dark matter in this first encounter is kind of shielding your stellar mass from tidal stripping. And then when your galaxy goes through a second close encounter, then it starts losing a lot of stellar mass. So this is basically why like nobody had proposed that thing with like the origin of the chemodynamical populations in the string is because the metal poor population, which was stripped first, is really like 1% of the stellar mass loss. And these stars are like really difficult to find, basically. So this is kind of the situation.
More questions? No? Thank you.